It's like we're always trying to peek behind the curtain of this bizarre quantum world, right? It can
Yeah.
feel so abstract, but there's been this recent discovery that really feels like we've gotten a genuine glimpse into how it all works.
It is a pretty remarkable finding.
We're talking about quantum entanglement today, and specifically this research out of the Institute of Theoretical Physics in Paris-Saclay. These physicists have basically mapped out in a complete way how entangled particles behave statistically.
Yeah. Quantum entanglement, it's been this kind of mind-blowing concept for a long time. You could almost picture it like two coins, right, that are flipped at the exact same time, and no matter what, they always land on opposite sides.
Okay, I'm see where you're going with this.
But we're not talking about just heads or tails here. It's about these fundamental quantum properties that are linked, and the wild part is that link holds strong even when the particles are incredibly far apart. You measure one, and boom, you instantly know something about the other. Einstein called it spooky action at a distance, and he wasn't kidding.
Right, and that spooky action is at the heart of what we're diving into today. So for everyone listening, our mission is to understand what it really means that these scientists have figured out the full range of statistical outcomes of entanglement. This isn't just theoretical either. We're talking game-changing stuff for things like quantum communication and computing.
Exactly. And we're actually living in this era that's being called the second quantum revolution, which is all about harnessing these, well, let's be honest, these strange but incredibly powerful entangled quantum states.
It does make you wonder, where's this all going?
Well, think about it. The first quantum revolution gave us transistors, lasers, atomic clocks. I mean, those were huge leaps forward that reshaped our world. And now we have entanglement, which is poised to have a similar impact, possibly even more profound, with things like ultra-secure communication networks, incredibly powerful quantum computers. It's really mind-boggling to think about the possibilities.
Let's break down entanglement a bit more, just so everyone's on the same page. Imagine you have these two tiny particles of light photons. They're created in this really specific way that essentially links their fates. We say they're entangled. Now, the wild part is you can separate them, even send one to the opposite side of the planet. But if you measure a property of one like its polarization, which basically means the direction its light waves are vibrating, you instantly know the polarization of the other photon. It's that instant connection across any distance that's so bizarre but also so incredibly powerful.
It really is remarkable. And what's interesting is that the strength of that spookiness, that entanglement, isn't always the same.
Right, there are different degrees of entanglement.
Exactly. It depends on how those entangled particles are created in the first place. So, going back to those photons, the way you generate them might make them more likely to be horizontally polarized than vertical, for instance. And that initial bias, that sort of predisposition they have, it ends up influencing the correlations you see when you measure them later on.
So there's kind of a built-in tendency from the start.
Right. And then on top of that, you have the choice of how you measure each particle. If you measure the polarization at a tilted angle instead of straight, horizontal, or vertical, well, that's going to change the patterns you see in your results, too.
So it's not just the entanglement itself, it's also how we choose to look at it that affects what we see.
Precisely.
It sounds like there are a few key things influencing what we observe in an entanglement experiment then. You have how strongly linked the particles are from the get-go, and then you have the specific way you choose to measure them.
Right. Even in a simple setup, you've got these basic factors at play.
And of course, quantum systems can get way, way more complex than that.
Oh, absolutely. I mean, you can have systems with many more properties involved, all intertwined, and that creates this amazingly complex web of correlations. And the thing is, these quantum correlations, they have this very unique signature. They can actually violate what we call Bell inequalities.
Okay, now we're getting into some serious quantum territory. Bell inequalities, those are.
Well, they're basically these mathematical rules that we expect to hold true if the world operates the way we normally think it does. Cause and effect, things only influence each other if they're close by. But when we see those Bell inequalities broken in an experiment, it means something truly profound is happening. It tells us that those correlations simply can't be explained by any theory based on our everyday intuition about how the world works.
So it's like proof that there's something deeper going on, something that goes beyond our normal understanding of reality.
Precisely. And it's not just a theoretical curiosity. The fact that these correlations are so different from anything in our everyday experience is what makes them so incredibly powerful for things like secure communication.
Right, and it's not just about observing those strange correlations, is it? The real breakthrough we're talking about goes a step further. It's about actually being able to use those correlations to understand, and even verify the quantum devices themselves. It's almost like we've developed this quantum X-ray vision that lets us see if a device is working correctly without having to take it apart.
That's a great analogy, and it gets to the heart of what's so exciting about this new research. It turns out that by simply analyzing the patterns, the statistics of the measurements you perform on those entangled particles, you can actually deduce certain properties of the system that produced them.
So just by looking at the results, you can figure out something about the device itself.
Exactly. For instance, you can mathematically prove that the outcomes you're seeing are truly random, which is absolutely crucial for secure communication. And what's really amazing is that you can do this without knowing anything about the inner workings of the device. You treat it like a black box, and the entanglement statistics themselves reveal information about its internal quantum state.
Okay, that does sound a bit like quantum magic. You don't need to know the materials, how it was built, none of the specifics, just those linked particles, and you can gain these fundamental insights.
It's pretty mind-blowing, and that's the idea behind what we call self-testing. It's crucial for building truly reliable quantum technologies. Because if you don't have to just trust that the device was built perfectly, you can have much higher confidence in its performance. And that's especially critical for things like, well, ultra-secure communication, advanced cryptography, the kind of applications where even the slightest flaw could be disastrous.
It's almost like a built-in security check.
Right, and these self-testing techniques are the foundation of what we call device-independent quantum information protocols. They're incredibly powerful because they don't rely on any assumptions about the devices themselves.
The research paper mentions that some types of self-testing are already possible. Like, scientists could verify all the possible states of a qubit, which is basically a quantum bit, the building block of a quantum computer. But it sounds like there were still gaps in our understanding, especially when it came to entanglement that wasn't perfect, wasn't at its absolute strongest.
Right. Previous work had mostly focused on what we call maximally entangled states. That's the strongest possible link you can get between particles. Thinking back to those coins always landing on opposite sides, it's like maximal entanglement.
Perfect correlation.
Exactly. But in the real world, entanglement isn't always so perfect. There can be some fuzziness in that connection.
So a bit less predictable.
In a way, yes. And what Victor Barisian and Jean-Daniel Boncal at IPhT have done is figure out how to fully describe the statistical outcomes you'll get, even from these more common, partially entangled two-qubit states.
So they basically cracked the code for less than perfect entanglement. How did they manage that? The paper mentions a mathematical transformation that sounds really intriguing.
It's a really elegant piece of mathematics, actually. Their key insight was to discover this fundamental relationship between the statistics of these partially entangled states and the statistics of the maximally entangled states, which we already understood quite well. They found this sort of mathematical Rosetta Stone that lets you translate the complex patterns from weaker entanglement into the simpler, more familiar patterns of the strongest entanglement. And it's not just a trick, it reveals a deep connection between these different degrees of entanglement.
So by uncovering that link, they were able to create this complete catalog of all the possible patterns you can get when you measure those partially entangled systems.
Exactly. And having this complete knowledge, it's really significant for a couple of reasons. First, it pushes forward our basic understanding of quantum theory itself. It tells us what kinds of experimental outcomes are even possible. And second, it gives us these incredibly robust testing procedures that can be applied to a whole range of entangled systems and measurements.
Which brings us back to making those quantum devices more secure, right?
Precisely. We can now develop tests that don't rely on trusting the physical parts of the device, which, as you mentioned earlier, can be incredibly complex and could even change over time.
They're not always stable, is what you're saying.
Right, but instead of worrying about all the intricacies of the hardware, we can just focus on the entanglement statistics coming from the device, and based on those real-time observations, we can be much more confident in its security and reliability.
So it's a shift in perspective from trying to control the physical hardware, which is really difficult, to analyzing those directly observable outcomes of entanglement.
It's a powerful shift. It opens up new possibilities for more resilient security protocols, for quantum communication, advanced cryptography, even for the next generation of quantum computers.
Okay, let's sum up for everyone listening. Scientists have essentially decoded a big chunk of the language of quantum entanglement. They've mapped out all the possible statistical results, even when the entanglement isn't perfect. And this is a huge deal because it gives us this new way to test and verify quantum technologies without needing to know every little detail of how they work inside.
It's like being able to judge a book by its cover, but in a good way. You get this guarantee of reliability just by looking at the results, the
And
outcomes.
it leads to these device-independent quantum information protocols that offer a whole new level of trust and security.
And it's worth emphasizing that this isn't just about building better gadgets. This research is fundamentally about understanding how the quantum world works, giving us new tools to explore its mysteries. It has implications for all sorts of areas of quantum science and technology, and who knows what other amazing discoveries it might lead to in the future.
It's a reminder that we're still really at the beginning of this quantum journey.
Yes.
This idea that we can build and rely on incredibly complex technologies just by observing how they behave, it's a pretty profound concept. Makes you wonder, what are the implications of this kind of trust through observation in other fields? How might our relationship with technology change if we can be confident in it without having to be experts in how it all works?
It's an interesting thought.
And are there other hidden languages out there in nature just waiting for us to crack the code? That's something I'm going to keep thinking about. Thanks for joining me on this deep dive, everyone.